Yeah, we can do different roles. We usually do well, later Okay, let's get started. We have quite a bit to try to do today, and give ourselves a chance. Hopefully everybody who wanted to get into this class got in. There's a lot of scrambling there at the end, but I think it worked out. If you still feel like it hasn't worked out, talk to me after class. Hopefully, too, you started looking at the homework 0 and started to do that. A lot of you have already submitted it. Maybe like half of you already have. That's great. Our TMs are going to get to work grading that right away, so you can have some feedback on that. And I've already put up homework 1 on the assignments up on campus. So homework 1's there. I'd say take a look at it as soon as you can, because there's quite a bit there. And the lectures today, well, starting with last Thursday, but today and this week are going to be very helpful in working on those things. So yeah. So today we're going to talk about loss functions. So remember what we've done so far. So we talked about like how do we even do computer vision. Talked about the challenges of it. We talked about like one of these possible ways of going about it, but why using k nearest neighbors, why it's not a great idea. Talked a little bit about using your data in smart ways. We talked about linear classifiers and how we could think about using these as like a score function for allowing us to do this classification. Remember, like we have some set of parameters and in our linear function, and we input our image, and then that gives us some sort of score. What we'd like to see happen is that the class with the highest score for this image is the correct class of the image. So, like if it contains a cat, we hope that the score for cat is highest. And I say hope because this was just kind of all setting it up, but without really like talking about how you would actually do this, how you would actually like change the parameters so that this was generally the case. And that's what we're going to do today. So we're going to talk about an approach to this that we use for training neural networks generally, and this is by defining what's known as a loss function, and then also the methods of optimization. Starting to talk about methods of optimization of this loss function. So that we can change the weights so that we get what we're looking for here. Namely, the highest score is the right class for the image. Okay. So, any questions so far what we're doing?
I had a question from last week. So you introduced the linear classifier. And so I was kind of curious if you had an easy task or a solvable task with the linear classifier, would that also be an easy task for a neural network? Or is there like when you would use one versus the other?
Yeah, like as long as you didn't, yeah, it would be an easy task for a neural network. As long as you didn't really come up with a really crazy architecture that would make it really hard to learn linear things. Like most of the interesting phenomena to learn is nonlinear, and so that's the point of a neural network is to learn nonlinear relationships between input and output. Or that's one of the ways to characterize that. And you can make them really nonlinear, especially with well, in particular with what activations you choose. So like a typical activation that we use is almost linear. We'll get to it at some point in the next couple of weeks. It's called a ReLU, or a rectifying linear unit. And it's basically it's linear on some part of its regime, it's zero other parts. So it's almost linear. So in that case, you're basically learning linear functions with a slightly linear, and they're very powerful for learning nonlinear phenomena as well as linear. So yeah, it would work. But as you learn more about this, you'll hopefully kind of see what I'm talking about when I say it's not totally you could make it really hard to learn linear stuff if you wanted to. Okay. Any questions?
Yeah, follow up on that. Would there be a data threshold or an instance threshold where if you had less, or if you didn't have a lot of training data, then you wouldn't want to go that approach, you'd be better off training data?
Yeah, so let me just briefly answer that. So the whole practice of data science, I guess, is being really aware of these kinds of things, right? So neural networks really work well when you have lots of data, like lots of labeled data in this case, in classification. If you don't, and the reason for that is that a neural network is, again, it's like a really flexible function from input to output, and through these methods that we're going to learn, you can adjust the weight so that it learns that relationship. Obviously, and think of this as like a parameterization. So a neural network is like a parameterization of this relationship. And you're just giving it data to learn this relationship. Well, because there's so many parameters used in a neural network, if you don't have a lot of data, it's a totally under-constrained problem. It usually is actually very under-constrained. And why these work even at all is a great question that we won't really dive into, but we'll just marvel that it works. But it's a really under-constrained problem. And so you might not expect to be able to learn a decent relationship with very little data. So in that case, what you really want to do is you really want to constrain the parameterization. So meaning the degrees of freedom in your model is very small. And if for some reason you think that it's, you have some reason a priori to believe that it's got a linear relationship, then you might start a linear model. You might try a couple different models that have, some simpler parameterizations, but that's a choice up to the data scientist. It's really the wrong-headed approach to think that neural networks are the right way to go for every single problem you're ever going to see, right? They work really well in certain situations and really poorly in other ones. And and that's not necessarily something we're going to try to cover, but just being aware of that and thinking about that as you come to each problem, what's the right tool to use here is the right thing to do. So you're going to learn something about deep learning, especially convolutional networks. This will be a tool in your tool belt, but it shouldn't be the thing you pull out every single time to solve every single problem, because that'll be wrong. All right, so let's start to motivate what it is we want to do with the loss function. So again, we're just going to have very simple examples, right? 3 classes, 3 images, and what we hope is the case. And here are the values coming out of our score function, whatever that score function might be. And what we want to have happen again is we want it to be the case that the score function gives us the highest value for the correct class. So this is not right, because the car is highest. This is right because car is highest. This is not right because, again, car is highest. And clearly it's a cat-car problem. So, we need some way of kind of characterizing that. So So we do this with what's known as a loss function. So a loss function, like it says up there, is some way of telling how good our the current classifier, or like the configuration of what parameters we have, how good that is for this problem that we're working on. And this problem, remember, is dependent on the data. So given our data set, and this is meant to be, you know, a pairing of like input, which in this case would be the images, and output, which would be like the correct label. What we want to do is we want to express some notion of like how well we're doing over this entire data set. So you know, here's our score function for the example I. Here is the correct label, and this loss function is going to take whatever our score is and whatever the correct label is, and it's going to output something that says something about how well we're doing. And a typical thing to do is to average all the losses over our entire data set. So that's what this sum and dividing by n is like. We have n examples in our data set. We'll calculate one loss per example, and then we'll just kind of average all that. I mean, you could do this in aggregation in a number of ways, but this is just kind of a standard way of doing it.
This might be a dumb question, but I see you have the subscript I for your L there. Does that imply that you could use a different loss function for different training?
Yeah, so yeah, that's a good catch. And the answer is yes. And really what that's trying to say is that like this is particular, like this loss is particular to this example. And you'll see, like it doesn't make sense like in the way that this is written, but as we go further in the slides, you'll see some other examples where it's like, oh yeah, I see why we're parameterizing that way. So, right. Yeah, so this is what we're doing. Why is it called a loss function? Well, the way this is set up is what we're trying to do here is we're trying to minimize the loss. So loss has kind of a negative connotation. So if there's any loss at all, then that's bad, and zero loss is good. So what is typically going to be the case is that the losses are going to be done in such a way that minimization, so like the smaller the loss, the better off we are. We might sometimes actually have negative losses, so like the more negative it gets, the better off it is. But often we try to put these in a regime where everything's non-negative, and we're trying to make the loss zero. And this comes from like notions of information theory and entropy, like how much information we're losing in this like particular encoding. Although this is stretching the analogy because it's not really that anymore. But that's where the word loss is. But loss negative connotation, the less loss, the better, is what we're going for. So let's consider a particular example of a loss. So this is known as a SVM loss or a support vector machine loss. So this is a loss used in a particular kind of machine learning model called a support vector machine. It's also known as a hinge loss. You'll see a picture of this in a second. But the important thing here is that this is just a loss that we could apply per data point. So so the setup is the following. So for our data point or example I, this is going to express our loss. So remember that I here is the yi is the correct label for our example, and then j is just going to range over all of our possible labels. So we just think of our labels as being like integers and 1 through 10 if we have 10 classes, and this s is the score that our score function is giving to that particular class. So we plug in our example, and remember it gives us a score for all in this, for example, 10 classes. So Sj is the score it gives for the jth class. So like S1 would be the score it would give for cat, for instance. S2 would be the score it gives for car, or frog, and so on. So it's just a way of kind of keeping track of how many classes we have and what the score is there. So that means that SYI is the score we've given to the correct class. Right? This is the actual correct class. And then we have all this kind of other mathematical stuff going on here. So let's look at this for a second. So what this is saying is the following. We're going to sum up, we're going to range over all of the incorrect classes, right? So this j not equal to yi is saying for all of the classes not the correct class, we are going to do the following. If the score of the correct class, so sorry, for the jth class, the jth incorrect class, if the correct score is greater than or equal to the score for the jth class plus 1, then that makes a contribution of 0 to the loss. So this is saying the following thing. If our score function is already for this incorrect class is already, the score for the correct class is already greater than the score for this particular incorrect class by a margin of 1, then we're like happy about that. That's not going to make any contribution to the loss. Okay? That means that, again, for this particular incorrect class, our score function currently is giving the correct class a score that's greater than this one by 1. And so we're happy with that. And this 1 could be kind of like anything positive, but 1's just kind of, I don't know, just kind of easy to deal with. You could make that 10, 100, whatever. It's called the margin in the SVM loss. And it's just some expression of like how much better you want the correct score to be than all the other incorrect scores. Is that making sense? Now what happens if that's not the case? If that's not the case, then we make a contribution to the loss that looks like this. So if this is not the case, then then this score is no longer greater than or equal to this. So if it's less, so it's less than that. So it's making some sort of positive contribution here. And we actually add that to here. So this is saying something like what we actually want is this, but it's not this. So like whatever is the difference here, put it here, right? We're just taking this and subtracting this off both sides. Put it here, and that's contributing something to the loss. And it turns out that you can also write this. So you're doing that for each of the incorrect classes. So each of the incorrect classes. So if they're all correct, if the score of the correct class is greater than the score of all the incorrect classes plus 1 for each one, then there's going to be 0 loss. Like for this example, we're in a good state. Otherwise, we're going to have some accumulation of loss here. And you can write this as a max. You can see that let's see. If this is satisfied, then if this is satisfied, then this term is negative. So the max of 0 and negative is going to be 0. So that's going to make contribution 0. And if it's not the case, so this is turned around, then this term is positive, and it's making some positive contribution. So it's greater than 0, so that would be the max. So it just turns out that's like an easy way to write that down. And you can kind of visualize this. This is why it's known as the hinge loss, is that you have, let's see. So this right here is like your possible scores S, Y, I, and as long as S, Y, I is greater than S, J plus 1, there's no contribution. But when it's less than that, it's going to start to make a contribution. And the important thing here is that like the less that's true, like the greater the contribution, the greater the loss is here, right? And that's sort of making sense. What this is trying to do again is trying to make everything like it really wants everything to be like this, and the more it's not like this, the more loss there's going to be. And it's called hinge loss, right? That's just like a hinge. Clever, right? Yeah.
So for SYI, it's the one of the ground truth escorts. scores will.
Yeah, it's the score for the correct class.
Okay, so what's the range for the correct class? Is it, for example, 1 and for the other 0? Or...
Well, the score can be anything, right? Like this is the output of a score function. Like if it's a linear function, it could be anything, right? We can range using a linear function. We can range from negative infinity to positive infinity.
The correct score, so there should be 1 class.
Yeah, but remember, all we care about is that this is like a relative best. We just want it to be the case that when we give it an example, that the largest score, it could be positive or negative, the largest score is given to the correct class, right? Like that's our criteria. That's how we're going to make our prediction. Is we're gonna give it an example. We're gonna look at all the scores, and we're gonna figure out which one's the highest score. And then whatever class that is, we're going to say, oh, this image contains an object of this class. So we don't care if that score is, 100,000 or minus 100,000 or whatever, as long as it's the largest one out of all the ones of all the scores that are being output by that score function. So it's relative to the other classes. And that's why we just talk about this criteria. We're just hoping to see this greater than all the other scores by some margin. Yeah.
So we're getting SYR from the training set, right? Not from the testing.
Yeah, that's right. Because we have the label in that case.
Yeah.
The training set will have the label.
Yeah. So in that case, for each and every class after training, we have to look at each and every class labels, and whatever the maximum value score it has set for the particular class, we have to take that as our ground truth.
I'm not sure I answered I understood the question. I just remember, like, whatever the score function is, like if you pick it to be linear, whatever your parameters are, this is just a way of measuring how well we are doing on the ith example, right? So it just is a way of measuring. There's lots of ways to do this. We're going to look at another example in a second. But it's just a way of measuring this. And this way of measuring is saying we want the correct score to be larger than all the scores for the incorrect classes by a margin of 1. And you can pick that margin to be 10, you could be 100. We just want it to be larger. If we don't want it to be 0 or negative, because that would make sense. But yeah, it's just a way of scoring this, or a way of like evaluating the score function. And it's like consistent with our notion of the largest score is the correct one. All right. Okay, so like how does this work in practice? So in this case we have 3 data points, right? So I goes from 1, 2 to 3. And then what we want to do is we want to calculate this for each of each of the data points. Yeah, what am I saying here? Yeah, we're going to do this for one of the data points here. We're going to calculate this Li. So this is like L1 here, the loss for the first image. So what do we do? So the correct class for this first one is cat. So like j is equal to 1. So we only want to calculate this for j equals 2 and j equals 3, or j equals car, j equals frog. So let's look at j equals car. So the incorrect score right now is 5.1, which goes right there. The correct score is 3.2, it goes right there, and 1. That's for the car class, and now for the frog class, we have the incorrect score is minus 1.7. The correct score is 3.2 again, so we subtract that off, add 1. Do the arithmetic, and we have, this becomes this becomes this. This is positive, so we get a 2.9. This is negative, so we get a 0. So the loss for this example right here is 2.9. It's not telling you much other than, like, we're not getting this right. Like, if it's not 0, we're not getting this right by a margin of 1, right? You can continue doing this for all the classes. In this case, it's actually the case that our score function is giving a score to the correct class. It's giving the largest score to the correct class. So you can go through and calculate this, for the incorrect class cat, the incorrect class frog, go through it, and you find out you get all zeros. So that's good. That's telling us that our score function is doing the right thing. It's giving us the highest score. It's giving the highest score by a margin of 1, and so forth. So this one's also wrong, and the loss there is 12.9. Okay, these are just numbers. These are just ways of like just encoding like how different we are from what we want. And like we're making this choice with what we want, right? Like a margin is a choice. We can have that margin be 0, and we sell something that kind of makes sense. But we're just choosing it like we want to be really sure about what we're doing here. So we want to make sure that this is the score larger by a score of 1.
Yeah. Is that 1 usually like a hyperparameter?
No, it's a hyperparameter, yeah. And it turns out like it doesn't really matter what it is. Like in a straightforward kind of classification problem, there's really no intrinsic scale, and that sets the scale. The margin sets the scale. So like you choose to be 1, like you now kind of have like a unit of 1 margin in there. If you set it to be 10, you have now like a unit of 1 margin. That 1 margin is equal to 10. It's like you're just sort of introducing units. It's adding a scale. Because like again, like what does the score even mean? No one really knows. We just want to have this property that it gives the highest score to the correct class. Okay, cool. So what's the loss? What's the total loss in this like really small data set? Well, we just we calculate this for like we just did for all of the data points in our data set. We just have 3, and then we average them, and it turns out that over our entire data set we have an average loss of 5.27. So what is this telling us? It's not telling us a whole lot other than like it's clear we're not getting some of the examples right in the way that we specified by this margin. So like it's likely that we could change the parameters and do better. All right. Okay. So let's think about how SVM loss works here. So what happens to the loss if the car scores change a bit? So just by like a little bit, like it's just kind of perturb, cat by a little bit, car by a little bit, and frog by a little bit. What happens to the loss? No, it's small. Doesn't matter which direction it goes in. Just know that it's small.
If the score of car changes a little bit, it doesn't matter.
Yeah, if the scores for if the car scores, so I should be a little more specific. These car scores, not these car scores. Maybe that is a little bit confusing. Sorry. These car scores. If these car scores change by a little bit, does our loss change? No, it doesn't, right? Because if it's already 0, we know we're already kind of, we know we're already in this regime where like the correct scores are large enough that if we just change them slightly, a little bit, this relationship is still going to stay true, that this score is larger than Sj plus 1. So this is just an interesting property of SVM loss. Like once an example is like correct, like it has loss 0, then small changes to the weights don't change that. That's kind of nice in some sense. Like you kind of want to get examples figured out and then like keep them figured out. It's bad though because it's like really insensitive. So like all of a sudden you have like a catastrophic change in the loss because like you cross some threshold and all of a sudden you have like a whole bunch of loss because of the scores. But in general, it's insensitive to small changes in the loss once the loss is 0. What's the possible min and max losses here? What's the min loss? What's the minimum loss here? 0, right? We get like everything satisfies the relationship we want. It's 0. What's the maximum? Yeah, we can have really bad weights, and we could just keep making them worse and worse and worse, and larger and larger and larger, make the scores as large as we want. That's right. Okay, at initialization, it might be the case that all of our parameters are small, in which case, because it's just a linear function, that means also our scores are all small. So what's the loss in that case? Okay, I mean, the one is getting there. We're looking at the total loss. Think about the total loss here. Okay, so yeah, if all the s's are small, then this term right here is essentially 0. This is a 1, so each of these terms is contributing essentially a 1. I mean, it's going to be close to 1. And how many 1s are there? In this case, there's 2, but in general, if you have n classes, how many 1s will there be? N minus 1. So each loss is contributing an n minus 1. Or sorry, each loss, but the loss for each data point is contributing an n minus 1 loss. So what's the total, or what's the loss over the data set, which is the average of all those?
Average should be n minus 1.
Also n minus 1. Yeah. So the loss there over the data set is n minus 1. Good. What would happen here if we summed over all the classes? So maybe you're sitting there thinking, like, why on earth are we excluding the case where J is the correct class, Y I? What would happen in that case?
We always keep having a 1.
Yeah, exactly. So in that case, when J is equal to Y I, this is equal to this, so this is 0, so you have a 1. So there would always be a 1 in each of these LIs. So the loss would, like the minimum loss would no longer be 0. It would be 1 times the number of, well, the average of all those 1s, so it would be 1. So your minimum loss now would not be 0 anymore, it would be 1. So you could do that, but it's just sort of like, why? It wouldn't change anything really. You just shift the loss by 1. What if we use the mean instead of the sum to do these LIs? We do use the mean when we average all of the LIs to get the loss over the entire data set. But what if we did an average here instead of just summing these all up? How would that change things? Yeah, good. Just would scale it, right? Like there would just be a 1 over n minus 1, like the number of things in this sum. And so that n minus 1 would just kind of come out and be, like whatever the loss is right now, it would just be scaled by n minus 1. So like, again, yes, it's a different score, but like the details wouldn't change. All of the relationships about like what's larger, what's smaller, like those would all be preserved. It's just some sort of scaling of that. Okay, what if instead of the term above, we squared that max term? How would things change? Yeah, good. Again, this is like an order preserving relationship, the squaring, right? So on the positive axis, so all of our scores are already non-negative, so that's what they're preserving. So like again, like all of the things we could say about it kind of are preserved. It's just that in this case, like very large. So larger losses would be even larger, and that kind of makes a difference when we start to think about how we optimize these things using gradients. So like there would be much larger gradients in this case, as once the value is greater than 1, they'd actually be smaller in the other case when you're between 0 and 1, and that would sort of change the dynamics of like how we do the updating of the parameters, which we'll get to, but. Yeah, for now, it just means it's basically the same when it comes to like thinking about what the loss means. Just kind of shifts the scale around a little bit. Okay, turns out this is like super easy to code up in Python. Hopefully many of you, if not all of you, especially after the homework, have familiarity with NumPy. NumPy is like a standard numerical library in Python, and basically like everything you want to do, kind of like numerical computation in Python, is done using NumPy arrays. Although there's obviously other libraries that provide their own data types, but This is like by far the one that's most used, and all of the deep learning frameworks that you could use right now kind of use these as they work with these data types, and it's really nice because it has all the like operations you'd ever want to do, right? So this is a very simple one where we have no bias. How do we calculate our scores? Our scores are just W times X, which is this is how you do this in NumPy with this dot operation. If you're like a MATLAB person and you miss just using your asterisk to do that. Actually, that is available in newer versions of Python, but still not standard. So some people are like, "Yay, that's great." And then so you get your scores. Now you use your scores and you compute this maximum. It's not the sum yet. This is just like all of the margins over all the scores. NumPy is cool because you can do this kind of indexing into it. It already does like appropriate broadcasting when it can kind of figure out the right dimensions to broadcast to. You can do this same thing, set margins, do these sums, you get your loss. This is not Python, of course, but the good news is like this is a vectorized way of computing this. This is very fast, and as you do the homework over the next couple of weeks, there's going to be a lot of like implement this kind of thing in a naive way. Now do it vectorized. Make sure you're getting like the same answers when it was naive. Make sure that it's the same, and then see how much faster it is. And there's going to be like multiple levels of like how to vectorize these things. So vectorized again means that like we're not doing a loop over all of the possible scores and like doing the sum, right? That's actually a very slow operation in Python. Loops are bad because it has to introspect the type of the variables being used. So sticking in NumPy and doing these vectorized operations where it's all kind of happening at once in the operation is way, way, way faster. The way that we want to think about doing things numerically in Python. Okay.
Sorry, will you repeat that about the for loop?
For loops are bad in Python. No for loops in Python. That's all. When doing numerical stuff. So because of the dynamic typing in Python, it has to introspect the type. That's a very slow operation every time it goes through the loop. You can of course speed that up. Like you can use Cython, and Cython you can type your variable for iteration. You can get past that, but like in general, it's really bad. And you'll see that. Like the homework kind of points this out, how slow it is to loop over things and how fast it is to do these NumPy vectorized operations. So for loops bad, NumPy vectorized operations good. All right. Okay, so let's keep thinking about this. So suppose that we actually do have a W where this loss over the data set, this average loss, is 0. Is this W unique? It's not unique. Why not?
Because the scores, we just say that the scores are better by the margin of 1. The margin could be 1, 2, or more than.
Okay, let's just say that the margin stays 1. So we can't change the margin. And we find a W that makes this loss equal to 0. Is that the only W? No. Why not? You're right. Why not?
So there can always be a better hypothesis, which can.
What'd you say? 2W. Yeah. You read my. You're right. 2W is also any multiple of this W other than 0. Here's an example. This isn't the proof, but it's an example. You can see that if you factor this out. Actually, sorry, not all multiples of W. All multiples larger than 1 will preserve the fact that this right here is still negative. And more importantly, when you add 1 less than 1. So there's actually once we find a great W that gives us total loss of 0, we can actually find a whole bunch of them. Is that a problem? Yeah. Question.
Well, so that itself justifies the fact that the margin doesn't matter, right?
Well, the margin matters. It just sets a scale.
Yeah, because you can always scale W to get a margin arbitrarily small or large?
Well, once you have a W that gives you it gives you loss. Yes, that's true, but that's not true until you find a W that's like that. And it may be the case. It may be the case that there is no W that can do that.
Yeah, like once you fix the margin,
Yeah,
there will always be a W.
That's right.
Fix it.
that's right. Once you fix the margin, and you can put a W with that margin, like a W that for that margin gives you a total loss of 0. Now you can do this trick where all these multiples of W will also give you the same total loss. So it's just a problem. The fact that we don't have unique sort of solutions to this optimization problem. We haven't even talked about the optimization problems, but there's apparently lots and lots of W's that will give you the minimum value here of loss equals 0. Once one exists. So is that a problem? Again, this is just true for this linear case. It's not necessarily true when the square function is nonlinear, like for all the neural networks we're going to look at.
So these functions aren't convex then, or they have multiple minimums then, or?
Yeah. Is that bothering you? If that's bothering you, you should get out of this class now, because neural networks have these large neural networks we're going to learn about have loss functions that have, who knows how many millions of local minima. These are the most non-convex problems I think that could possibly exist. We're gonna look at models that have tens of millions of parameters in them, and it's super non-convex. So for all of you who know something about optimization, you should already be feeling what? This can't work. And you're right. Theoretically this can't work, and yet somehow it works. So I don't know that we'll talk a lot about that. I don't know that I have an answer for why it works, but the truth is it works. This is this horribly empirical nature of neural networks. It's we're going to have very few theorems here, and yet you're going to have one of the most powerful tools for doing things like image analysis. Look, I'm glad you brought that up, because I just wanted to assure you that this is the worst situation you could be in, and yet things still work. And this is just a linear function. So it's because of the nonlinearity of the loss, right? The loss is no longer linear. The loss is nonlinear because of this max and the way that we're composing these things. But we're just using a linear score function. This gets worse when you have nonlinear score function. Okay, where was I before getting off on that tangent? I don't remember. So there's all kinds of minima to this loss function. So what you can think about this in the following way. We're going to start talking about optimization, I promise. But you basically have you have some sort of loss surface. This is a bad drawing, but this is W. This is your parameter space, and there's all these local minima. Sorry. In this case, they're all at 0, so it should be something like this. So it turns out there's once you find one, there's all kinds of these. So the question is, does that matter? Should we think about which one of these we actually got, and should we try to get a different one? So yeah, that's the question. How do we choose between W and 2W, or 3W, or 100W, or what? So this gets us into the area of what's known as regularization. So, so the loss function so far is just about telling us how well we're doing, how well the score function is doing in terms of something that some way of measuring that makes sense, using our SVM loss. Okay, but it's apparently not really constraining the W's in any way. So does that matter? Well, it does matter a lot, actually. And the area where this kind of fits is known as regularization. Regularizing, or smoothing out our parameters. So how does this work? Well, in practice, what happens is we have our loss function ends up being at least 2 pieces, and if we're doing really awesome stuff, we might have lots of pieces. But there's always a piece that expresses how well we're doing at the problem at hand, and then there's another piece that expresses our preferences about what the weight should be like. So it's kind of like it's trying to like choose one of the out of all those possible sets of weights, a certain, it'd be nice if it was just like one set of them, but like a certain set of them that have some sort of properties that we think are desirable. So what does that mean? Well, what I've written there is prevent the model from doing too well on the training data. So, oh yeah, there's a new hyperparameter that we've added now, this lambda, which is like, in this sum, it's sort of balancing the relative, again, it's like another scale, the relative scale between our model, our loss on the data, and then like how important our regularization term should be relative to that. It's always about scale here. Okay, so remember what we're trying to do. We're trying to minimize this loss, right? So minimizing this to 0 means that we have like perfect classification on the training set. And then we want this thing to basically like at 0 kind of express something desirable about the weights. And one thing that you see a lot are these very simple examples of regularization that are known as like L2, L1. So in L2 regularization, this is like we've treated, it's like we've treated all the weights as like one big long vector, and we're taking we're looking at the length of it, like we're doing a dot product with itself. We're not doing a square root here. You could do that, it just again changes the scale of what lambda means. But it's some expression of the fact that like how big the weights are. So if I square every single weight and I just sum them all up, this is saying something about how big the weights are, generally. And if I want to minimize that, that means I'm just expressing a preference for having smaller weights. So instead of it being 2W, I want W, or however small, we might want to make that, which would depend on our choice of lambda. That's like L2, that's like a Euclidean idea, Euclidean norms, all the geometry that you're pretty much used to. But you could choose this to be very different. Another standard way of imposing regularization is this L1 regularization. So instead of the square of each weight, you take the absolute value of each weight. Again, you're getting a positive term here, and making it smaller means that the weights are getting smaller. And if you know something about the differences here, we kind of mentioned it the other day, but this tends, the difference between these two is that this tends to make your weights dense, meaning that like all the weights are usually going to be non-zero in a case like this. But in a case like this, you're actually promoting the sparsity in the weights. So like a lot of the weights, as long as the regularization strength is strong enough, are going to be pushed to 0. So it's like you're promoting lots of zeros to be in there. And then, hey, you know what? Why not just combine them? That's called elastic net for some reason. I have no idea why. And again, look, we added another hyperparameter beta. That again is like expressing, the scale of this term and this term and that term. So there's always got to have a parameter in there to kind of say how strong or how not strong you want these to be. There's definitely way more complex ways of doing regularization, especially with neural networks. We're going to talk about some of these ideas. Dropout and batch normalization are like really important ideas in regularizing neural networks. I won't say what they are now, but we'll talk about them later in the class. There's also like lots of other ways to regularize. There's a couple of names here that we won't actually talk about in this class, but just know that like this is a big area of research and interest because there's basically so many solutions to this problem, and we're trying to like pick out a best one. So like why in the cases of like L2 and L1 do we want the weights to be smaller? Well, or just why regularize at all? Well, like I've been saying a million times, we're expressing preferences for weights. Like this could basically encode anything you want about the weights. If you like, you could pick up all kinds of, you could choose all kinds of goofy things, and as long as when your regularization term is 0 when it is those things, then like you can put that in there. It's just differentiable. You're going to be able to do all the optimization you want, and it will like do that. making the weight smaller makes the model simpler in terms of like how wiggly, or like the total variation that your function can what's the right word, can achieve on your data set. And I'll give an example of a figure in just a second. So this is actually really important. This is like how it's really easy with lots of parameters, especially in these huge neural networks, to overfit to our data and then not generalize well to our test data, right? Like it's learned like the exact relationships between the input and output in our training data, but it maybe have learned that so well that it doesn't do well in the test data. So by like smoothing out the parameters, making them simpler, then we usually do better in terms of generalizing to our test data. And truth be known, some of these functions are just so nice that we never have a convex problem, but we can sort of like make things feel a little more convex by adding in these like convex terms, and gives it like nice curvature for doing the kind of optimization that we're going to do, which is great to say. Okay, so here's a question for you. So here's our data, 1, 1, 1, 1, 1. 1, 1, 1, 1, just 1, 1. And we have two weight functions. This is very simple, right? Just like one class here. This one here, where there's a 1 and a 0, 0, 0, and this one where it's all 0.25, 0.25, 0.25, 0.25. So notice that when we do the dot product, this is like doing the w times x part of the score function. Notice that they both give us a 1, right? So they give us exactly the same score. Okay? So they give us the same score. They're, like in this very simple case, they're equivalent. Let's say that we are doing L2, like we got an L2 regularization term. Which of these two choices of weights that gives us exactly the same score does this L2 regularization term prefer? Which one does it give us a lower score? Yeah, exactly. So this is, in this one here, you'd get I think I had this one. You get a 1, right? Because you square the 1 and all the rest give you 0. So you get a regularization score of 1. But if I put these in, I'm going to get the square of a fourth, which is going to be less than a fourth. And I sum up 4 things less than a fourth, I'm going to get less than 1. So it's actually smaller. That term's actually smaller than 1. So this regularization term prefers to see solutions that look more like this, that are like, this is what I was kind of saying earlier, like that the weights are kind of smaller and more kind of spread out amongst all of the possible weights, rather than like all concentrated in a single class in this case, or a single entry. Okay, so what does it mean for first input models? So if you've probably seen this like in many other classes, but like if you're fitting polynomials to like wiggly data, you might get, you can keep using higher and higher order polynomials, and you can like fit this data actually very perfectly. But that usually means that like if I now have a couple of test examples from the same distribution, they're going to be way off here. Like there might be one kind of coming from right here, but this like really overfit function f1 is giving us a score way down here. And that's just because like there's just noise when you sample from your data. There's noise coming from just like the intrinsic generation of the data, but also like when you're subsampling from your samples, you have you're not seeing all of the distribution, so you're kind of missing some of these things out. So oftentimes, if I don't have this here, but like if you're fitting these polynomials, you'll see that like the coefficients of these polynomials, they get larger and larger and larger to fit like more and more curvy things. But if you sort of force those coefficients of the polynomial to be small, you get far more like smooth or less bumpy behavior, and that usually generalizes better. It's not like a guarantee, but it usually performs better. So this is like one of the reasons why we deal with these things. Oh yeah, gotta have this So now we have these other test points, and they lie closer to the regularized curve in this very data set. Okay. Questions about that? That was a crash course in regularization. We'll keep talking about regularization. So we're going to talk about cool forms of regularization like about patch norm and things like that that are specific to neural networks. But that's just kind of, crash course. Any questions about that? Yeah.
So we are assuming here that the model which lies behind the data is a simpler one. What takes the model itself is
it's kind of like an Occam's razor type of like approach. Like if there's two models that like fit the data kind of relatively relatively similarly to each other, we'll usually want to take the one that's simpler. So like simpler in this case would mean like smaller weights. It would do less lumpiness, less variation, less total variation.
So basically, to summarize, you wouldn't want like a weight for a feature that's like 100,000 along the others are 25, because perhaps for that training data, that feature is very important for a certain prediction. But you might have something on test data that has that feature that doesn't necessarily have that prediction, so you want to cool it down a little bit, be less extreme.
I mean, yes, that's exactly right. I mean, this is just definitely a heuristic. This is not like everything will always, it'll always be better if you do this. It's just, it'll mostly be better because you tend to overfit. Like it's very easy in highly parameterized models to overfit to the data. Like the more degrees of freedom, the more parameters, the more degrees of freedom you're giving to the model, the easier, like the more chance it has, like the higher dimensional space it has to be able to match everything. That's obviously bad because it just can't be that all the rest of the data lies exactly in those places. So you expect it to be close to the data but not right on it, and so you sort of smooth things out by reducing the weights, and voila, you generalize better almost all the time. But there are definitely situations where that would.
And just to go up on that, that's why you have the hyperparameter lambda, and then cross-validated. It's just basically you're looking for how much you want to be simplifying this model.
Yes, and and I'm glad you used the word cross-validation, because what you don't want to do is use your test data to figure out what your hyperparameters are, and then use that same test data to see how well your model's doing. That's called overfitting of the second kind. So overfitting of the first kind is trying to choose, trying to regularize, like we've been talking about, try to make things generalize well. But you never want to use the same data to both make a conclusion about your model and then make a decision about your model and then evaluate how well it is. That's bad. That's also overfitting. So this is why when we did we talked about cross-validation last time, we take our training data and we split that up into these different folds, and we do cross-validating on these different folds, leaving the test data totally out. We pick our hyperparameters on that, and then we go and measure our generalization error on the test set that we haven't seen yet. That's just basic ML 101, But just that's not so specific to neural networks. That's just if you don't do that, it's clear you shouldn't be hired to be a machine learning person. But it's pretty easy to learn, because you do the first time you really screw up doing that, you feel really stupid, and then you never do it. Actually, that's not true. People make mistakes over and over.
Okay. So does that mean the regularizer you just kind of go against with overfitting?
That's right. Its main job is to prevent overfitting.
So is it just try to minimize the effect of?
So the way we typically want to express this is we want to have a term when we add to the loss, so that if it's 0, that means that our weights are doing the thing that we want to be done. In practice, that doesn't happen, right? Because there's a competition between these two terms, right? The one is trying to give you good classification. The other one is trying to make your weight small, which has nothing to do with classification, right? So they kind of compete against each other, and then this is the lambda in there, that regularization strength will determine how much each component is contributing to the total, what we get out of the weights in the end. But yeah, the one is trying to help us classify well, the other one's trying to make our weights small, or like prevent overfitting in some way. They're usually competing against each other. There's usually some optimal region in which to like balance that, and that's what we use cross validation for. Okay, a couple more questions, we're gonna move on.
Okay. So in some applications, people use dropouts instead of the regularizers. So is there any reason?
Yeah, that's why I said dropouts are another regularization term. Another way of regularization that we'll talk about when we
So
start
how do
doing
you
it.
compare with each other?
We won't be talking about that right now. We'll talk about that when we get to convolutional networks and talk about that.
The different measures for regularization L2 and 1, these are just different in their application, or
They're just different ways of expressing what you want. Like, if you want, like between L2 and L1, if you want them to be sparse, you pick L1. If you want them to be dense, pick L2. And if you want there to be something in between, you pick elastic net. Or you can pick any LP measure as long as P is greater than 1, and like you get something. Like you can put anything there. You get to play.
the second question is there any situation that the weights can be all 0 when that is the minimum for the class and the weights are all?
Yes, that would be an extremely uninteresting problem, like for linear score, right? Because that means all the scores would be 0 all the time, right? So usually, 0 weights means zero scores for everything. So your problems usually set up that way, so you don't get like these very strange things happening. So what that means is, yes, the one term is trying to make all the weights 0, but the other term can't have all the weights being 0 because you would not get good loss. You would not get good classification. That loss would skyrocket as you like make the weights too small, right? So it's a balancing act between them. Yeah. Any more? Okay. All right, so let's look at another loss function. Here's one that we use quite a bit. Margin losses are used. The DSPM losses are definitely used, but more in like areas like what are known as like metric learning, where we'll get into that. Metric learning. This loss is used when we're doing classification almost exclusively. This is called softmax. So what's happening here? So we still have our scores. You see the S's are there. We still have our scores. What we're doing is we're basically turning them into a probability distribution. So the way that we do it, you can do this a number of ways. The way that we do this is we first exponentiate all these. So the first transformation is to take this and make this the exponent of e. So like e to the 3.2 ends up being this, e to the 5.1 ends up being this, e to the minus 1.7 ends up being this. And we do that because that makes all of our scores positive. Makes them all positive. Once they're all positive, then we can just divide by the sum of all of them and get a probability distribution, right? Meaning all of the entries are non-negative and they sum to 1. So now we have a probability distribution. Why is that good? Well, I sort of mentioned this at the beginning of the class, but it's really, really useful to express your problem in probabilistic terms, as if we're trying to sample from a distribution, or we're trying to learn like the maximum of a distribution or something like that, like maximum likelihood estimation. If we can put these things in the probabilistic terms, then we often have like a lot of like ways of reasoning about this problem that make this that give us more tools to kind of work with. So in this case, these original values that are coming out of your these original scores are sometimes known as log probability relations. You might have seen that before in statistics or something. So what happens here? So the loss that we end up using in this case is the negative of the log of the probability. We interpret this as a distribution. The probability that our class is the ith class given the y ith class, so like the actual label given the input xi. So, and when there's a lot of these slides that say log. Well, it doesn't really matter which log you use, but we typically think of just using the natural log because we've exponentiated this with e, like the natural number e. So that's natural to use natural log, but it doesn't, like, in some sense the properties are preserved no matter which base you use. So so in this case, so the negative of the log of the probability. So that might kind of seem weird, but let's think about that for a second. So this is the probability. So for this ith example, this is the probability that the class, like given our score grid, this is the probability that the class is the first class cat, that the class is the second class car, and the class is the third class frog. And then when we put it into here, we get this number here. So why the negative log? Well, there's a lot of reasons why, but like one of the first things to think about here is all of these values are going to be between 0 and 1. And for any log, in that region, the log is negative, right? So it goes from negative infinity up to 0, between 0 and 1. And then when we take the negative of that, we get that makes it positive. And then the loss is larger when the probability is smaller, right? So, and what we really care about here is just the probability for the correct class. We basically want to maximize that probability, which means in this particular way of doing the loss, the negative of the log, it's minimizing the negative of the log of that probability, because that's going to be moving it towards 1, where the log is 0. Okay? This turned out to be actually maximum likelihood estimation, in like straight up maximum likelihood estimation. And the way that this is done is that you, the way that you express this loss function is you have this probability distribution right here, and then you have like the correct one, right? So this is a cat. The first entry, corresponds to cat. And so what we do want is the probability to be 1 here, and the probability for the rest of the class to be 0. So we want this distribution to look like this distribution right here. So there's a number of ways to think about how to measure the difference between those. That's going to be our loss. And this gets into ideas from information theory. Who knows about the KL divergence? Know something about the KL divergence? Maybe you've seen this before, maybe you haven't. This is a very useful way of measuring the difference between two probability distributions. In particular, it's 0 when they're equal almost everywhere. These are discrete probability distributions. That means everywhere. And if they're not equal, then it's a positive number. It ends up not being a metric. That's why it's called divergence, not like a distance. But it's very, very useful for measuring the difference between these two. In particular, it's not symmetric. You can see this is what the KL divergence looks like. It's this funny term of probability times a log of this quotient, and you can see that P and Q are not interchangeable here. So it's not symmetric, so that's why it's not distance, but it's still very useful for measuring the difference between two distributions. And this is related to something called the cross entropy, which is just the divergence. So the cross entropy between two distributions is just the divergence of the KL divergence between them plus the entropy of the first one. This is these are ways of measuring, they have measure theoretic or information theoretic interpretations, but for us, they're just ways of measuring the similarities between distributions. And I'll just leave these in the slides. I won't go through these super carefully, but just know that there's a long history of what all these things are. So there's some notion of the entropy of a distribution, which says something about how surprised you are when you draw something. So it's largest. So I don't know how long this gets. Somewhat hard to explain in a short amount of time. It's just some measurement of how like non-sure the distribution is, like how non-deterministic the distribution is, like how like concentrated this is around like like some of its states. And what's nice about this is it has like really nice kind of analytic properties that we'll use over and over again. And again, I'll just leave these in the slides. You can kind of go through these and look up these terms and kind of learn about them. But I just said these things about the KL divergence, why it's really great to use for measuring differences. And we end up using the cross entropy when we're doing loss because instead of having this kind of goofy term in the quotient which can cause us problems, like if it's 0. Actually, there are zeros everywhere. Or there are problems with zeros everywhere because this would be like an infinity, which is quite a lot of loss. But this term ends up being like a lot easier to work with. It has good properties for like gradients and things like that. And it's just like again, it's just you just kind of go through these derivations. It is just the entropy of the probability distribution P and the KL divergence of P and Q. So it's very similar to the divergence. So it's also measuring the difference between these distributions. And once you have these things, you can go through and look at these. What's nice about this is if you calculate the cross entropy between these two distributions, where P is this distribution and Q is this, you're going to do here. Let's see. Should I have that there? Well, the point is that you have these zeros here, which get rid of all the terms that are the incorrect class, and you have one term left with this one. Remember, there's that P out in front, and you get exactly this term here, which is the maximum likelihood. So if we use the cross entropy to compare the two distributions, we actually get the maximum likelihood estimate that we thought was a good idea from the beginning. Okay, I'll stop right there for a second to see if there's likely questions. See if there's any questions. Or maybe I just blew through it so fast you can't possibly ask any questions.
Actually, I found that the KL divergence is also the same here.
Yeah, it is. And this has nicer properties when you don't use this like absolutely sure distribution for your label. Like if you know there's some noise in your labels, a way that you deal with this is to like allow there to be some non-zero probabilities here and then subtract it off of here. And the cross entropy has better properties for that because you're summing it. The entropy term is also contributing something, which when you minimize that, like I don't know, it has better properties when we do gradient descent. A good observation. Just know that what's happening here is when we use softmax and we calculate these distributions, what we're doing, the contribution to the loss from each particular sample is this negative log of the probability. And the way the reason why we can kind of get away with that and not think about the other probabilities is as we minimize this, we're maximizing this probability, which is also at the same time removing probability from the rest of the classes, right? So so if we maximize the one class that we care about, that because these have this constraint of having to sum to 1, the rest of the probabilities are decreasing on the rest of the classes. It could be the case that some of this, as we do this, some of this probability actually goes into here, right? So a particular class might actually increase in probability, but the total probability in the rest of the incorrect classes has to be going down because the probability of the correct class is going up. Okay. Yeah, this is another loss function that we'll use all the time in classification. It's got wonderful properties, and you'll see as we go through more and more of those classes, like the probabilistic interpretation of this really is helpful in posing and thinking about this problem and extending the problem of classification to other types of problems. Okay. Yeah, so let's go through this. What's the min and max of this loss? L1 here, or sorry, Li. So what's this softmax? What's the minimum? What's the maximum? Negative log. So the minimum is what? 0. Good. Maximum is? It's infinity again. So remember, it's this is this is our log function. So like this is 1, this is 0, and we're just concentrating on this range right here. And when we take the negative of it, it looks like that through this range. So this goes all the way up to infinity. So our max is infinity and our min is 0. And again, what's important about where 0 occurs is that occurs with probability, like when the argument is equal to 1. And that's what we're trying. So making the loss 0 makes our probability 1. That's what we're going for. So good. That's right. At initialization, all the scores will be approximately equal. What is the loss in that case? So like we're like in this random state, so like all the scores, like no score should be preferred over the other, so they're all essentially the same. What does that mean for this case? Yeah, exactly. So it's the probability, like so essentially like the distribution is just going to be uniform, 1 over n, however many classes we have, and I have to see here, but n. So yeah, in the case where 10 classes, you'd expect to see this. And this is maybe this seems goofy to kind of just go through this, but like this stuff, I use this, and like people who do this kind of thing use this stuff all the time to troubleshoot your massive neural networks, especially at like initialization. Like you want to see that like when this thing is initialized, that you're getting like whatever the appropriate term is here out. Otherwise, like something weird has happened, and like usually, if there's problems in networks, it's usually around like initialization or something like at the beginning, not like during training. And you can usually see that if you just run some of these examples. Okay. Yeah. So like in this particular case, if we use the SPM loss, we get a loss that looks like that. If we use the softmax loss, we get a loss that looks like that. They're both non-zero. They're both expressing the fact that like we don't have exactly what we want for this particular example, but they're very different from each other. Okay, so let's ask a question like we asked before. So suppose I take a data point and I jiggle it a bit. So this is like like slightly changing the values, the scores. So what happens to the loss in both cases? So starting from this case right here, where this says the class is 0. Like you've been saying 1. Anyways, this is the correct class. So what happens if I change things a bit? Well, we kind of already talked about this for this example right here, right? Like if we already the loss is already 0 and we just change the scores a bit, it remains 0. And if it's not 0, then it will change slightly. But what about for softmax? What happens when we change the score slightly for softmax?
Anybody out there? I'm trying to answer this.
I think one of the scores that changes slightly, but for the second row it changes more than the third row.
Yeah, so like if you go through, like if you think about these examples, that's right. So like each of these is giving you, like you're putting you in a different place where it might be more or less sensitive to changes. But in general, small changes to the scores, here translate to small changes to the score, to the loss, right? Like these are all very like continuous, even differentiable, like no elbows in the functions or being composed here, right? So like the score is linear, exponentiation is just nice and analytic. This transformation to make it, a probability distribution is nice and analytic. The log is nice and analytic. So like So like small changes in the scores give you small changes in the loss. Everything's very smooth there. The fact that we have this hinge for the hinge loss, for the SVM loss, means that like we have regions where like there's no sensitivity at all, and other regions where there is. And you know, that doesn't mean a whole lot, but it does matter. It actually does. So what it does mean is that like every data point is going to contribute some loss to the loss function. It might be much smaller than other losses, but it's going to contribute something. And when we do gradient descent, like all of the data points are going to give us some signal on which we'll be able to like walk on along the gradient, which is what we're going to get to next. But that's not the case for the SVM. There are certain data points where that won't, that won't contribute anything to the loss, and including no gradient to the loss. So like that matters, and this is like that matters when we're doing optimization, and that's one of the reasons why we actually use softmax, because we need a lot of signal to do the gradient descent. So anyways, that's what we did today. And the next time we meet, we're going to be talking about, okay, how do we finally find this best W? So, we have a way of thinking about how good our W is. Now, how do we use that loss function, that measurement of how good W is, to actually update it and get a better W? That's what we'll do next time.